This is lesson 2 of the first unit. I'm looking at page 8 of the notes, and partway down it says a function fails to be differentiable at x equals a for a variety of reasons. I want to start with some drawing. Let's make sure my pen works here. So in this particular drawing, I'm going to make a function that's like this, and it continues on forever to the left, but it's not smooth here. And this has a mathematical name, believe it or not, just called a corner. So a corner is a point where it's not smooth. We might draw another one, a traditional V shape, perhaps like an absolute value or something. So these are both examples of corners. So the question is, let's first write corners. Corner. Question is, mathematically, what's happening to make it a corner? What's happening to not let it be smooth? The fact that it's not smooth at these corners makes it not differentiable. But we can see, let's pick another color. We can see that the slope here is approaching, let's say like positive 2 or 1, something positive. But as we approach from the right, slope is approaching a negative number, perhaps -5. So in order to have a corner, we say that the two one-sided derivatives are different, and that's a new terminology, and that's what the top of the page is describing. So if we take a moment to go to the top of the page now, and I'll scroll down to resemble the top of the page, and let's go back to white. It says that the limit as h approaches 0 from the right of f of a plus h minus f of a all over h, provided that that exists, we're going to give it some notation, and this notation is not in your text, but it is standard notation, and I'll write f prime at a, but this is approaching from the right, so I put it in the sub, and it means the one-sided derivative. And likewise, f prime of a from the left means the limit as h goes to 0 from the left of f of a plus h minus f of a. This is like one of the examples we did in lesson 1, but just now giving it some formal notation. So coming back down here to the corner, we can say it's a corner if the following occurs. We have f prime of a from the right, and also f prime of a from the left, both exist. And at the same time, or but, f prime from the right is not equal to f prime from the left. Not equal. If that is the case, you have a corner, which is what is shown here in the drawings. Next, we have what's called a cusp. Now, cusp is like an extreme corner. It comes up and goes back down. Perhaps if you were drawing like a bird, a seagull or something, you might draw it like that. Now, what makes this cusp different than the corner is the fact that not only do the two one-sided derivatives differ, but this slope, you see, maybe this is positive 2, and then it's positive 5, and then positive 10, and really large, really large. This is actually approaching infinity, positive infinity. And as we approach from the right, it's approaching negative infinity. So it's an extreme corner. So the criteria mathematically for this cusp is that f prime of a from the right approaches positive infinity, and at the same time f prime of a, as we approach from the left, is approaching negative infinity. So that's one way we can have a cusp. Or, on a flip-flop, f prime from the right of a approaches negative infinity, and f prime of a, as we approach from the left, approaches positive infinity. So if you have the first bracket or the second bracket, you have a cusp. Finally, we have what's called a vertical line tangent. So let's see if I can draw this appropriately. That might not be good enough. Let's see if we can explore. If I drew it right, there should be one point where the actual tangent line is a vertical line. So we approach from the right, it's approaching positive infinity, and from the left, it's also approaching positive infinity. An example of this might be something like y equals the cubed root of x. Comes down, does this, kind of like that. So mathematical criteria for it is as follows: f prime from the right of a approaches positive infinity, and at the same time f prime, as we approach from the left, is also positive infinity. So that's one case. Or we have the case where they both approach negative infinity, like I have written here.